to have them here to teach us how do we accelerate our code development so that this is the rules, that we have to electrify. Now, Alexi?
Sure. Hi, can you hear me?
I can. Hey, Alexi, can you share your screen?
Hi. Oh, you know what? And I even have a camera. Oh, no, I can't. Never mind. Feel free to turn my camera on if you want or not. It's all the same to me, but hello. And once I have the ability to, I will share my screen. I think I need to be granted the option to do that.
Who can share? All panelists can share. Can someone?
So down at the bottom, Alexi, there's like a little green button on your bar.
There we go.
Share screen. You'll click that. Yeah. Woohoo.
Now am I showing the right one? Big open slide without much in it?
Yes.
Just zeroing in on buildings.
Perfect.
Great. Hi, everybody. So yeah, thanks for having us on, and Sean, thanks for that fun intro. I'm Alexi Miller, Associate Director at New Buildings Institute, and we have a couple other NBI folks on. We're going to give you a quick rundown in the next 45 minutes of some updates on these three leading decarbonization initiatives. Amruta Khandolkar is going to start talking about the Advanced Water Heating Initiative, and then I'll pick it up and talk about the Grid Optimal Buildings Initiative. And Kathy's going to bring it home, our research director, to talk about the Building Electrification Technologies Roadmap.
Woo!
Without further ado, off we go. Amruta, I'll run the slides for you, so just let me know.
Yeah, thanks, Alexi. Thank you, Alexi, and thank you, Sean, for such an inspirational presentation. I am all excited to make a difference now. So I am Amruta Khandolkar, New Buildings Institute. I have been managing Advanced Water Heating Initiative for almost 1.5 years now, and excited to be here presenting today.
Great. Amruta, this is Kathy. Can you hear me? And everyone out there? Great. Hey, Alexi, can you change your view so we see just the slideshow and not the next slide?
Oh, am I showing the wrong screen? Yeah, I'll go ahead and do that. Go ahead.
There's a click up at the top.
Yep,
yeah.
I'll get that.
Okay.
Thank you.
You're welcome.
Kathy. I still see it the same way, Alexi.
Yeah, go ahead and keep on going, and I'll do this while you talk.
Okay. Next slide, please. So, you typically, when you hear about decarbonization or electrification, people talk about grid side electrification and decarbonization, but space heating and water heating are heavy users of natural gas in a building, and just these two end uses account for 87% of carbon emissions between residential and commercial sector. So so there needs to be like special attention given to these two end uses. Next slide, please. And through the Advanced Water Heating Initiative, we are focusing on the water heating side of things. So Advanced Water Heating Initiative, it's a regional multi-stakeholder effort to help increase production as well as adoption of heat pump water heaters. It's a collaborative effort. It's a collaborative market transformation effort between New Buildings Institute and Building Decarbonization Coalition. Next, please. So I wanted to, why heat pump water heaters? Why so much focus on heat pump water heaters? Heat pump water heaters are proven technology and are in the market for more than for decades now. Compared to conventional gas water heater, they are 2 to 4 times more efficient, and that's why, and because of that, they also reduce greenhouse gas emissions and as well as methane emissions. And of course, a grid connected smart water heater has great ability to reduce demand. So to reduce demand when connected to the grid. And act as thermal batteries. So that's why there is this focus on heat pump water heaters under Advanced Water Heating Initiative. Next slide, please. The funders of the initiative, funders and partners of the initiative is Bonneville Power Administration, Southern California Edison, Northwest Energy Efficiency Alliance, SMUD. Next. So So right now in California, 93% of California's water heating stock and 50% of Northwest water heating stock is directly pumping fossil fuel into the buildings while for heating water. And just to give you some context, that is equivalent to 14 million water heaters in California and millions of water heaters nationally. So just this technology alone has tremendous opportunity to reduce carbon emissions. So what you see on the screen is a theoretical model developed for this initiative. It's a market transformation pathway. And the green line is high efficiency, low carbon heat pump water heater adoption. And the focus is on next 10 years, so from 2020 to 2030, emphasizing to make heat pump water heaters the mainstream. Next slide, please. So role of the initiative. There are many efforts happening under this initiative, but I like to bin them under these three main categories: strategic planning and coordination, priming the market. So anything to do with market demand and confidence building activities are under priming the market, and technology advancement and validation. So making sure that the technology is advancing, is available, and at the same time there are supporting materials available like trade community, like guidelines and checklists, permitting guidelines. So the third bullet covers anything to do with technology advancement and validation. So we have 4 different working groups under the initiative. Of course, with the initiative leadership, which is focusing on planning strategy, and we have a 13-member steering committee. So for the working groups under unitary heat pump water heaters, so just think about these working groups as technology, like focusing on technologies as well as market sector. This initiative is for residential as well as commercial buildings and new construction as well as retrofits. So so under unitary, there is this 240 volt working group, 240 volt unitary, which is led by Owen from SMUD and Jareen from Southern California Edison. And I would say each working group, since the technology is in different phases of the adoption, each working group has their unique challenges. For example, the 240 volt, the product exists in the market, and this working group is focusing on developing building demand. So program, utility incentive program guidelines and recommendations, regulatory recommendations. The next one, which is 120 volt, which is led by Jim Lutz from Hot Water Research. The product is not in the market right now. The product is not market ready right now. I know Craig is presenting from GE. So GE has a 120 volt right now under UL testing. So since the product is not market ready, this working group is focusing more on like technology development, guidelines development, and building market demand. So building market demand. And the central heat pump water heater working group, which is led by BPA. So for them, the challenge is central. If you think about central systems, those are custom systems based on the building type, the number of occupants. But with the custom application, it is difficult to have market adoptions, quicker market adoption. So this working group is focusing all their efforts on making this a packaged system. So just think about it like the market transformation with VRF systems. Having a package system normally helps with market transformation or quicker market adoption. Finally, the connectivity and controls working group, which is led by Jeff Wicks from NIA and Ram Narayanmurthy from EPRI. They are focusing on recommendations to these different technologies, working groups on demand management recommendations to these different unitary central technologies. Next. So for the advanced water heating initiative, we focused on what are the different program pathways that from adoption perspective and fuel switching perspective. So new construction, of course, is and again, we are thinking of these pathways parallelly and not sequentially. So new construction with unitary central and under retrofits, electric resistance to heat pump water heater, just because of the ease of adoption, compared to gas and propane, where panel upgrades are required. And finally, the central heat pump water heater. Next. So key updates. This Advanced Water Heating Initiative is a collaborative effort of over 35 organizations and 50 plus active members. The key stakeholders are manufacturers, efficiency advocates, utilities, and cities. Great news is JA13 is adopted. It's a heat pump water heater demand management standard that requires time of use based load shifting, which is for non-connected units, and grid connected load shifting. There is a great potential for this initiative to be a national initiative. We have received interest from state of Colorado and Midwest. And we are in fact starting a similar effort in Midwest. And so I would say a few, like last year, there were many downstream programs. There are like 18 plus heat pump water heater focused programs in California and 80 plus programs in the Northwest. And none of them were seeing much of an uptake. They were all downstream programs focusing on customers. So now we see that there is a switch from downstream to midstream programs, which is focusing on distributors and contractors. And with that switch, there is slowly, as we are starting to see an uptake. So just to give you an example, Southern California Edison, they just came up with their retailer incentive program. Now they have units available for $199 at Lowe's, like at retailers like Lowe's, and most of the units were sold within 1 week. So I think that's a great progress. Next slide, please.
Thanks, Amrita. About 2 minutes out of 15 here, by the way.
Okay. So quickly on the logic model, I do not plan to go through the logic model. Basically, the logic model focuses on the barriers for the technology adoption and then channelizes between these three main channels: market channel, programs and partnerships, and regulatory. And then there are activities and outputs to make sure to tackle the barriers. Next slide, please. This slide just shows how those different activities that are happening, the technology advancement, as well as the market development activities that are happening, are for next 2 years are going to finally 2022 is going to be. They are going to have these activities are going to happen in parallel, and 2022 is going to be focused on market rollout. Next. So we think for this market transformation effort to be successful, we need to know clearly, what is the energy emissions as well as operating cost savings by this technology compared to its competitors like electric resistance to gas, standard gas tank and condensing tankless, as well as non-condensing tankless. So this is just a draft. We are starting to look into the energy as well as emissions. Next slide. So what you see here in this graph is the green is the heat pump, the emissions potential, like emissions from these different technologies, whereas the orange is the operating cost. The yellow line is with off-peak operating cost, and the orange line is with the peak operating cost. And something some interesting finding is heat pump hot water heaters, if they need to be like optimized, and if not used with advanced controls and grid connectivity, then they can in fact add operating cost for the customers. So advanced controls and grid connect, there is a great emphasis on advanced controls and grid connectivity. Again, one feedback I received from the steering committee is doing this over a range. So I'm working on high versus low variables, and next time we'll have a range for these. Next. And finally, yeah, so we have advanced water heating webpage, and the link is given below. And also, next slide. And also a blog that is out by Kathy Higgins and me. Kathy Higgins, our research director, and me. So feel free to read that. That's at the link below. So yeah, so that's about Advanced Water Heating Initiative. The key takeaways are, I would say, the heat pump water heater is a proven technology and ready for market adoption. And there needs to be more emphasis given to this market adoption and technology like technology advancement with grid connectivity and advanced controls. Thank you.
Thank you.
Thanks, Amrita.
You know, I see a few questions. This is Kathy, and maybe it would be great just to have them narrated by Amanda now, or so they're right in line with Amrita. It's a long time till the next one.
There's a question here. Does the Rheem 120 volt heat pump water heater not meet the standards that Amrita was talking about? If not, why not?
So Rheem is not specifically talking about their 120 volt water heaters, and manufacturers are very silent about their new products, as you can imagine. So, and because they're not talking about their products, I don't know about their specifications and whether it meets the standards or not.
Well, I can share with you. They've said they're going to give me one of their 120 volt products and install it in my house with like Maples Plumbing locally. I've been waiting for this to happen. And my understanding is this tank is a 12,000 BTU per hour. Our current products are 4,500 BTUs per hour, so essentially 3 times as much compressor, no electric resistance. Electric resistance has been 12,000 BTUs per hour of electric resistance in there. So this heat pump, under reasonably optimal conditions, will make the same amount of heat as the electric resistance on full blast. So they're essentially the same amount of heat production is going to come out of this machine. But this 1 ton, it sounds like they need a dedicated 20 amp line, 120 volt, but 20 amps. So that's like the kitchen circuit you have, that much power, as opposed to a normal plug loads, which might be 15 amps.
So is it a plug and play or not? Is it a...
No. So getting a dedicated line, a dedicated circuit is not plug and play. But it's definitely better because you don't have to change your panel. At least it's low power, but you still need to get a line to it.
So you are talking about their hybrids that they came out a couple of months ago, and not the 120 volt. Is that correct?
I'm talking about the 120 volt, not the hybrid, but instead it's just 120 volt, no electric resistance backup, and it just needs needs a dedicated circuit because it's using enough electricity at 120 volt that it can't, like, it's not using 900 watts, which would allow it to fit on a normal circuit. Instead, it sounds like it's using 1400 or 1600, something like that, and so it needs a dedicated 120 volt line.
Okay, cool. More to get from
yeah, your work is bearing fruit. Thank you.
Any more questions?
There was another question. Does the 40 million water heaters in California include non-residential water heaters or just residential households?
So the 14, sorry.
No, you're fine.
I was just saying that the 14 million number is including residential and residential, residential and non-residential. So multifamily is included in that number.
Do you know what portion is commercial water heating?
And by commercial, if you mean multifamily, then I do. I have those numbers not off the top of my head right now.
Okay, maybe you could look in the chat and then respond to that question.
Sure.
And then I did have one more. Are the water heater manufacturers prepared for a large surge in demand from the REACH codes in 30 cities taking effect, do you think?
Yes, and we have had multiple conversations about regulatory, and that aligns with the regulatory channel that I showed in the logic model. Yes, I think there is, because of those 30 cities with their REACH codes, electrification REACH codes, there's a lot of momentum around that regulatory channel as well. And water heater manufacturers are waiting for more such REACH code adoptions.
This is Kathy. Let me just add to that question from Jose on that. since the REACH codes primarily apply to that no new construction may be built without a penalty or with gas at all, if it's a gas ban, there's absolutely zero barriers in new construction to heat pump water heaters. Existing stock is abundant, a wide range of manufacturers. It's the retrofit, like Sean is talking about, where we're trying to solve the panel and power availability and supply. So onward. That was a great question.
Woohoo! Thank you, Amruta.
Thank you. Thank you all.
Looks like some more questions are coming in. I don't know if you want to get in the chat and answer them, and then
We have another chat at the end.
Okay,
We just thought we'd
Sure.
give her a chance, so let's right and fresh. Okay, thanks.
Or while the topic is still warm, if you will. So this is Alexi. I'm going to talk for a bit about the Grid Optimal Buildings Initiative, which you know, there are many strategies that we need to be thinking about for building grid integration, which is something we need to be thinking about if we want to actually achieve grid decarbonization as well as building decarbonization. So we have been working on an initiative for a couple of years now that I've been leading. It's jointly led by NBI and USGBC, called the Grid Optimal Buildings Initiative, all about improving building grid integration. I'm not going to spend a whole lot of time on the basics and the intro stuff, because I know this is a pretty technically savvy audience. So just very briefly, you know, I think we're all aware that the electricity grid used to be really a one-way street. Big thermal central power plants put electricity out there, used by buildings, factories, offices, and so forth, homes, factories, offices, and so on. In the future, we are expecting to see a scenario that's really, we're starting to build this. We have already started, and we are building this scenario where we have an interactive grid. There are two-way energy flows. There are renewable resources, both big central wind farms and utility grade solar, and we've got distributed energy resources on buildings, whether that be energy generation like solar panels or batteries. We got smart devices, we got EVs plugging in. It's more complicated, it's much more dynamic, and it's much more decentralized. So the goal here of the Grid Optimal Buildings Initiative is to make sure that buildings are doing everything they can to support our transition to this vision. One of the key drivers here that's pushing us to think about this at all is that the number one way we are decarbonizing the electricity grid is by adding more wind and solar. Awesome. But those resources are variable. Solar produces when the sun is shining, wind produces when the wind is blowing. Those have seasonality, they have daily variation. And so, for example, here in California, what this shows is carbon variation. This actually, I think, is back from 2017, and it's getting more and more so every year, which is good. But, you know, spring, you see lower carbon hours when we got lots of hydro in the mix, and when the wind's blowing. There's more demand in the summer evenings, so there's more, the carbon intensity on the grid is higher then. So we got some variability to play with. This is driven by both supply side things like lots more wind and solar on the grid, whether distributed or central, and demand side things like higher peak demand in the summer evenings or the winter mornings. You can kind of play this game a couple different ways. And the idea of what I mean by play this game is try to minimize building carbon emissions in a time of use manner. But if we want to get to a lot of zero energy buildings, then there are a couple different options you could take to get there. This is a slide that NREL, National Renewable Energy Lab, and Rocky Mountain Institute put together a little while back, a year or so back, sometimes called a tale of two buildings. On the left is a zero energy building focused, on the left is a zero energy building, and on the right is a zero energy building. The one on the left, however, basically got there by putting a bunch of solar panels on top, whereas the one on the right got there through a mix of deep energy efficiency, demand flexibility or load modification, where they're shifting some energy use from certain hours to others, and then a smaller amount of solar panels. So those upper two graphs with the golden load shapes, the golden areas, let's see if we can see my mouse. The golden areas are the building's load throughout the day. The green line is the solar PV generation. The blue part below that is the net load that goes through the meter. So that's what the utility sees. You can imagine that if you have lots of these zero energy buildings, which is something we want to have, of course, it is easier to make the grid work for all these buildings and to serve all these buildings if more of the buildings look like the one on the right than the one on the left. There are a couple different ways you can get there from here in terms of building modifications to change the load shape or the demand profile of a building. That's the kilowatts passing through the meter compared to the time, kilowatts over hours. Just plain old energy efficiency it continues to be critical. It's been foundational for a long time. It's still foundational. If you lower your energy demand across all hours of the day and the year, well, that lowers it at the peak too. That's helpful. You can also shed load. Traditional demand response programs more or less do this, right? Turn off your compressor for 15 minutes or turn down your lights, whatever the case may be. And that's usually used in traditional DR programs. You send out a call, some amount of the people who get the call do the thing, and some load is shed on the system. It's usually pretty short-lived, right? 15 minutes, 1 hour, sometimes up to 3 or 4 hours. Load shift is when you take some load and move it somewhere else. You could do this by pre-cooling or preheating, for example. Batteries are good at doing this, thermal energy storage. And then the last one, modulate. This is very short-term load modifications like frequency response and other grid ancillary services. The DOE likes to think of these things. This is a graphic from the US DOE, and they call this shift, they call it shed, shift, shape, and shimmy. It's another way to think of these. You can get to doing that, those are outcomes. What do you actually do in a building to get there is obviously a pretty critical question. I like to think of there being a couple different pathways to do that. One, there's permanent efficiency. Add more insulation, say, reduce your building energy loads throughout the whole year. That's helpful for peak, that's helpful for high carbon hours. Great. Peak shifting, design a building so that its time of use is shifted over time. Maybe you put on some west-facing shading so that there's less afternoon solar heat gain, and on a permanent basis, that building is just going to have a lower demand during those hot summer afternoons, which is helpful during the peaks. You could do a more dynamic approach, whereas the west-facing shading is pretty passive. You stick it there, it's there forever. You could dynamically put in maybe phase change materials or more thermal mass so that you can pre-cool the building and coast through that evening summer peak. And then you could be dispatchable and have two-way communication with the grid. Maybe you use a battery, maybe you do some other cool stuff with your building controls, HVAC, lighting, other controls. What we're trying to spark with Grid Optimal here, maybe spark is the wrong analogy. What we're trying to charge up is getting the design industry, the buildings industry, to think about these issues during design. So instead of just saying, okay, well, baseline used had an EUI of 55 and our design case has an EUI of 35. Great. I mean, that's good. But also, it's good to think about the load shape throughout the year, over the day and across the whole year. So we did some interesting modeling where we looked at how building design measures can change the load shape. This is out of some work that we did in collaboration with a group called Redcar Analytics. Here's a baseline code compliant new construction building in San Francisco. You can see the loads broken out into these various categories: cooling, a couple other smaller ones, lighting, plugs, etc. Summer day in September. If we then we came up with a bunch of strategies, things you could possibly do to adjust that load shape. Things like a little bit wider thermostat comfort, set points out a bit, morning preheating in the winter, afternoon pre-cooling in the summer, adding in some thermal mass, shading, all kinds of cool stuff. And what we found is that you can not only reduce that peak demand by 45 or so %, you also change when the peak demand occurs. So if your building has solar, that's great because you've now tuned your building's load shape to better match that solar. So you're maximizing your self-consumption. There's some good benefits to the grid to doing that, and of course for the building and the cost that it might pay in certain rate scenarios. So I want to go back to this just briefly, and I want to get a bit more concrete with this so that I'm giving you guys you folks some info that hopefully you can take and run with. remember how the carbon intensity of the grid varies over time. Here's California. Well, we did a grid optimal pilot project in Sonoma. It was the Sonoma Clean Power headquarters building. They retrofitted a 1970s office building to be deeply energy efficient and took into account time of use energy efficiency as part of that. So our role was identifying things like this picture you're seeing here. When should we be trying to target time of use energy efficiency, and then working with the design team to say, so what can we do about that? What we did was we took that carbon profile on the grid, and then we took the building's projected load shape out of the energy models and we multiplied them together. So what you see here, you might call the marginal building carbon emissions profile. It's over the whole year, based on the building schedule and its model, what are the carbon emissions from grid delivered electricity associated with this building's operations? You can see when it turns on, right, 5 or 6 a.m., somewhere in there, the building starts up for the morning, and then it really comes on after the sort of pre-start. It really comes on around 8 a.m. And there's two big areas that we're looking at: winter morning warm up and summer afternoon and into evening. So we focused on strategies with this design team that could address both of those periods. Some of it is traditional energy efficiency, air, sealing, insulation, that kind of great stuff that we can't leave behind when we get into this fancy stuff because it's still critical. And some of it is maybe a different take, like pre-cooling and enabling the pre-cooling both in terms of the controls and in terms of the thermal mass and HVAC systems in the building, so we can actually pull that off. I mentioned that the variability in grid carbon intensity is going to grow. Well, here's a look from NREL. 2020 is now in Colorado. This is all Colorado right here. And we think by 2050, you can see very clearly when the sun comes up in this graph. So being able to play this game in design is important now, and it is going to be increasingly critical. And you can imagine when the grid profiles are looking like this, here's the carbon. Well, there's not a dissimilar situation going on in terms of projected cost. So at some point, that's going to filter down into rates in Colorado and across the country. The shapes are going to be different. The specifics are going to be different. But as we decarbonize the grid, there are many reasons, carbon foremost, but certainly many more, that we need to be thinking about this as designers and engineers and people in the industry in general.
Can I interject with a question?
Yeah, sure.
The 2020s here. Now, this is using electricity as resistance, is how I'm sort of thinking of this. Like, if I was using resistance, this would be the carbon intensity of that electricity at different times of the day and the month. And if I was using it as a heat pump, I might see, maybe like 1/3 of a decent heat pump system. On average, 1/3 as much energy being used. When I asked Martha Brooke to do that at the Energy Commission, she did a similar graph to this, and it became much greener. Do you think that would be the case with this graph now, if you used like a 300% efficient heat pump?
Well, so that's what this one takes into account, the efficiency at the building. This is building times grid here.
Okay.
So yes, it got much greener. I mean, the color scale on this one is a little different from the color scale on the California one. These are just illustrative. But yes, bringing the heat pump into play is critical for being able to actually reduce the emissions in a significant way. That's, the story of electrification, as Kathy is going to tell us in a little bit here, is in great measure the story of heat pumps.
Thank you. Sorry about that. Appreciate it.
No, it's a great point, and it's critical. Yeah. So just a quick note on grid optimal before I pass it over to Kathy to bring it home. We're in the 3rd year out of 3 on grid optimal. We have developed some metrics that define how buildings interact with the grid and put a number on the quality of building grid interactions. There's a blog up there that's linked. We got a white paper out, Summer Study 2020 this year, describing them in detail, documenting the methodology and all that fun stuff. We've done several pilot projects, and actually just last week, I'm happy to announce we got approval from the lead Energy and Atmosphere Technical Advisory Group for our pilot credit based on these metrics. So there, once we jump through a few more hoops, there should be 3 lead points available for grid optimization based on the metrics that we've developed over the last couple of years.
Woo-hoo.
Woohoo! Yay! Awesome. And these are the metrics. I'm not going to go all through them in great detail, but I want to note that the first three, I can't even find my mouse. It's somewhere in there. That's all right. Grid peak contribution, on-site renewable utilization efficiency, grid carbon alignment. Those are all about comparing the building's load shape over the whole year to what's happening outside the building, whether that's megawatts on the grid or whether that's carbon, those variabilities. It's kind of like, how well does this curve stack up with that curve? And you roll it up over the whole year. There's some integration and some math going on there. But basically it's how well, the first one is how well does your building align with peaks and exacerbate or help alleviate grid peak situations. Similarly for grid carbon, are you adding load during high carbon hours, or are you optimizing for carbon? And then some of the ones toward the bottom, the demand flexibility metrics, for example, as well as resiliency, they have more to do with what can you do at the building? What kind of capabilities do you have? Do you have the ability to trim load when it might be helpful? That kind of thing. So there's just a note there. You know, we are still accepting pilot projects and would be interested in talking more if folks would like to. Maybe a brief moment for a couple clarifying questions, but I don't want to eat into Kathy's time too much.
Yeah, you have about 10 minutes for Kathy here, and I do want to respect her as well. So maybe you could take questions. There's like 4 or 5 good ones here in the chat. Could you just type in there and transition?
Oh, that's a great idea. And I'm targeting less than 10, so we'll have a moment there too. Good idea, Sean.
I'll answer
Great
anything.
facilitation, isn't it? No, we like Sean's.
Yeah, thanks, Sean.
Take care.
Okay, I'm going to grab the screen from Alexi because I'm going to navigate my own slides, as is my style, as my audio. Sean, is it good?
Yeah, it's perfect. You're doing great.
Great. Well, you like my opening picture. Can you see it?
You look lovely.
It's your photo that on the right that I'm hoping you'll enjoy.
Oh, yeah.
Thank you.
Emily Higbee took that photo, one of our staff. She's both an engineer and an artist. It's great.
Oh, I saw her on your
Great,
website.
Emily.
Well, thank you for having MBI join you in this great effort of all of ours professionally to improve the built environment towards decarbonization. I'm going to move through what Sean said was a lesson-focused approach and cover just 3 topics regarding a project I'm leading called Building Electrification Technology Roadmap. Better, great acronym, love using it, and I'm doing it on behalf of California. I'm going to hope that in 8 or so minutes you understand why better and what technologies are ready today and what their energy emission savings. If you can get that from 8 minutes, that's ahead of the average person for sure. You can see the partners listed here. Building Decarbonization Coalition and MBI are doing a lot of things together these days, and the California utilities, along with our research partner, IRIP and IPRI. So why buildings? You all know the CARB and California targets for 2045. This is a little bit older, 2050. We've got to drop these emissions to meet the targets. And it isn't about some governmental or bureaucratic target that's really just a wish in the sky. This is about really changing our built environment for the next generations. And this is the logo I've adopted, better now than later. So we really have to not wait. And we are today, my coworker just was telling me, she was reading that we are today having the implications of carbon that was released in the 1990s and the turn of the century. And so what we do today is affecting that period. The carbon that we can reduce, although you feel it's a slow movement, it will make a change in the future atmosphere and environment. So you see on the left here that buildings themselves within the California goal are 70% need in terms of how many buildings need to be electrified. And that means that 30% of buildings need to get electrified by 2030, and 70% of all the buildings need to be electric if the decarbonization goals in aggregate are to be met. So in terms of the emissions impact, again, the buildings are about a quarter. You know, everybody thinks it's all transportation, but we're in the built environment, it's a significant player, and efficiency remains a big part of that. Also, when we talk about the emissions impact of buildings, most of you smart people on the phone know that includes the materials. Someone mentioned embodied energy, but really the measurement of emissions has to do with the construction and the production of the materials. So that even when you look only at the framework of the building, working at operational energy reduction, which we are with building electrification, that's still 10% of the pie on the right. So buildings as a whole, from production through to operation, what we do at the building is a huge part of reducing emissions. I think a lot of people are familiar with the fact that gas is a major part of the use. So I liked that Sean opened and Alexi was next, because we're talking about decarbonizing the built environment, and a green grid is not enough. So you saw in Alexi's grid optimal, he's talking about changing the grid profile. Well, we can PV our way all the way to 100% clean generation, which has those problems of the time of use, but it's not going to change the fact that 70% of the residential energy use is met by natural gas. So unless we address emissions in parallel with the grid and the building, we're not solving the problem. And I just want you to be aware that it's so regional. If you're talking about residential gas and electric in Sacramento, well, water heating is 28% of the emissions, and space heating is 65%. But you get down to LA, down here on the right, water heating is over half, and space heating is a smaller proportion. So your location matters in terms of the prioritization of technologies. But the best thinking is just to think to get it all electric. But I think it's important to know the data. I'm just a little more data than as beautiful visual as Sean is, but here's some data also to make that point also. You may say, oh, look, 30% of commercial buildings use is natural gas. We've got to go after 30%. Well, in restaurants, it's 60%. In retail, it's only 8%. And that's just a ratio of the building type. But if you were to say, over the state's total use by building volume and square feet, the red bars would be your first priority. So make sure that you're thinking about this dynamically and about where the big targets are, because we can make larger change quicker at a couple of key sectors first. So what is this better that I'm working on supposed to do anyway? It's supposed to tell us what the technical status of the products are, where are they on the road to adoption, and what can we as efficiency professionals do to overcome the barriers to adoption? That's it. The target audience is efficiency programs and governments. It doesn't speak to all parties, but it will be informative to other people like design firms and manufacturers. And in order to develop better, we had to get into a thing we call the matrix. Alexi's favorite image here. And that matrix is where we looked at 4 end uses as seen on the right, 38 total technologies. Only those technologies, let me clarify, there are an enormous number of electric technologies. These are only the priority technologies that displace incumbent gas technologies. So that was the screening criterion. We have 2 vintages. We were comprehensive in new construction, retrofit, and 5 sectors. And we measured them across 5 parameters: their readiness, their availability, are they easy or not when put into the field? Think of those as site barriers. And we want all the scores. I've made them light gray because I don't want you to have to bother looking at those, but we want the score 3 to always be better, back to that acronym. So a high score is good and a low score is less available or less ready. Awareness, how aware is the market, and how impactful are they on greenhouse gas emission reductions? And this would have to, as you can imagine, be compared to other comparable electric technologies that would displace gas, because every single one of those is significant compared to using a gas technology at the site level. So the emissions profiles of gas are such that replacing it even with an electric resistance water tank, which is not good efficiency-wise or operational costs to the occupant, still has great greenhouse gas reductions. So we have to look across a number of parameters, but the emission reductions are compared to other technologies. And I'm just going to pause on this for just a second because I'll move to interpreting it. But what we've done with those scores, which come out of that matrix in a whole bunch of iterative questions and queries, really fun tool for us geeks. But we had to roll it up in a way that it was a little more intuitive to look at. So across the 4 end uses here, I don't have laundry showing, which Sean gave us some input on our laundry section, as a matter of fact. We have these 5 parameters, the matrix scores, And we have some Harvey bullets telling us if they scored high, medium, or low. So to that second learning for you today is what's ready now. It's these two items on the right in this matrix for space heating that are readiness and product availability that tell you first, can I go get it? And is it technically prepared for installation? So here's a quick glance at just a cut sheet, if you will, on single family homes and low-rise multifamily homes, where we take in the analysis a baseline of a gas baseline technologies, we do a step up to better technologies, and we're targeting the best technologies. And I'll add here that I might have to change heat pump dryer to condenser combo, because that is really, there's a combination of what's the best that's available and most likely to be adopted because it's price point. There's the best in just in terms of the best equipment you can use. And the combi system that Sean talked about really is the most attractive. Because of that, for example, I'm going to put these X's over glass radiant. Even though incrementally in terms of a step up in emissions reductions and a step towards all electric and affordability, it's a good choice. We actually, as efficiency people, have learned our lessons, I hope, from some of the past technologies we've promoted that just are not operationally great. Early CFLs, for example, and ballast problems and humming and early burnout. We want to go straight to induction. We have got to not hamper our own progress by introducing technologies that the occupant or user is going to be dissatisfied with. So let's keep an eye on the big picture and the higher opportunity. And from Sean's residential guide, for example, as Alexi said, heat pumps are the story of electrification for water heating and for space heating. And that's because of this 2 to 5-fold. 3 is probably the average COP, 3.5. That's 3 to 4 times more efficient than the gas technologies they're replacing. Energy reduction combines with reduced emissions, gets emission reduction at the grid. If your electricity is made by combined combustion turbines, gas-powered generation, and then emissions at the site. Got a double win with heat pumps. Last item of learning, what are the energy and emission savings? What do we need to have compelling data about in order to make the case? So here's a summary of 4 climate zones, cities in California, the single family model with that medium efficiency you saw, and the single family with the green far right efficiency. And I just draw your eye to the fact that these are all over 60% savings at each climate zone and over 80% emission reductions for emissions. These are just amazing and compelling amounts that will help us have the catalyst information to help change the market. So as a closing, I'll just remind you, a green grid is not enough. Buildings have to be combustion free. There's lots of great resources. There's no shortage actually of homes and commercial buildings in our California resources that are all electric already, including developments. Here's a shot of my home city. We got to work at our city levels and continue to advance the REACH codes and decarbonization policies. And we got to work at the downstream with the owners and decision makers and design teams, as well as with midstream supply chain. 3-pronged approach, all buildings, all electric. Thank you.
Hey! Thank you, Kathy.